Chapter 19 Electric Charges, Forces and Fields. Here is an overview of Chapter 19. We will first talk about electric charge, then move on to insulators and conductors. We will then talk about Coulomb's law, the electric field. We will see how electric field lines help us represent the electric field. We will then talk about shielding and charging by induction, and the final topic will be electric flux and Gauss's law. The effects of electric charge were first observed as static electricity. Here we have an example shown by this picture where we have an amber rod that when you place next to some paper on the table, not too much happens. If you then rub the amber rod on some fur and put it near the same paper, we find that the paper actually lifts itself off the table and is attracted to the amber rod. Charging both amber and glass rods shows that there are two types of electric charge. If you put two amber rods near each other, and in this case they both have a negative charge, you find that there's a force that tries to make the amber rods repel from each other. If you then put an amber rod next to a glass rod, and in this case the glass rod will have a positive charge, we find that there's actually a force that's attracting both rods together. All electrons have exactly the same negative charge. The charge on a proton has the same magnitude, but it has an opposite sign, which will be positive in this case. The magnitude of an electric charge is given in coulombs, and it has a value of 1.6 by 10 to the minus 19 coulombs. The electrons in an atom are in a cloud surrounding the nucleus, and the electrons themselves can be separated from the atom relatively easily compared to the constituents of the nucleus, which are protons and neutrons. Here we have a diagram which shows the electrons moving around the nucleus. The nucleus itself occupies actually quite a small volume relative to the volume that the electrons move within. Coming back to our previous example, what is really happening is when we rub the amber rod on the fur, some of the electrons from the fur get transferred to the amber rod. This makes the amber rod negative and the fur positive at the same time. To finish on electric charge, we must note a number of points. The first is that the total electric charge in the universe is constant, which usually means that in any sort of interaction or reaction, the electric charge has to be conserved. You have to have the same amount of electric charge before something as you do after that thing has happened. The electric charge is also quantized in units of E. What that means is E, this 1.6 by 10 to the minus 19 coulombs, is the smallest value electric charge can take. The next smallest value is twice that number, the next smallest value is 3 times that number, etc., etc. We should also note that when an atom loses an electron, it becomes positively charged, and we refer to this as a positive ion. When an atom gains an electron, it becomes negatively charged, and we refer to this as a negative ion. Moving on to insulators and conductors. A conductor is a material which the conduction electrons are free to move throughout that material relatively easily. Most metals are conductors. An insulator is the opposite. In this case, the electrons in the insulator cannot move around from atom to atom so easily, and most insulators are nonmetals. If a conductor carries excess charge, that excess will distribute itself evenly over the surface of the conductor. Here we have an example where we take our negatively charged amber rod, we place it near a metal sphere, some of the electrons are transferred from the amber rod to the sphere, and once they are on the sphere, the electrons themselves can move easily, and they move in a way to separate themselves as far away from each other as they possibly can. There are two other types of materials. We have semiconductors, and these have properties that are intermediate between conductors and insulators, and those properties will change depending on their chemical composition. Another class of materials are photoconductors, and these are materials that become conductors when light shines upon them. Moving to the next section, which is Coulomb's law. Coulomb's law essentially tells us mathematically what exactly the force between two charges are. It's given by the equation F is equal to K times Q1 times Q2 divided by R squared, where Q1 is the charge of the first charge, Q2 is the charge of the second charge, R is the distance between the charges, F is the force that we're interested in, and K is a constant, and in SI units this constant is 8.99 by 10 to the 9 Newton meter squared over Coulomb squared. The force between the charges is along the line connecting the charges, and as discussed before, this will be attractive if the charges are opposite and repulsive if the charges are the same. Now we will use some diagrams to demonstrate where the force, in the case where we have two charges, will point. In the first scenario, we can see we have a positive charge on the left and a positive charge on the right. There are two force vectors involved in this process. We have a force vector on the first charge, which is pointing to the left, and we have a force vector on the second charge, which is pointing to the right. The important thing here is the magnitude of each of these vectors will always be exactly the same, and that is given by Coulomb's law itself. And the direction will be as shown. For the second scenario, we have two charges. One is a positive charge and one is a negative charge, and we can see that the force vectors will point towards each other, which is what we expect when there's an attractive force. In this instance, as the previous instance, the magnitude of this force vectors will be the same, and that magnitude again is something that you get directly from Coulomb's law. The final example is shown on the bottom, and here we have two negative charges. Again, we have a repulsive force. We can see where the force vectors will point, and the magnitude of these force vectors will also be exactly the same for each of these charges. If there are multiple charges in the system, the forces will add up by superposition. Forces are vectors, and on the left we can see an example where we have the force on Q1. It has a contribution from a force from Q2, a contribution from a force from Q3, and a contribution from a force from Q4. You have three vectors, three forces acting on this charge, and to get the total force, which is shown on the right, one has to do a vector sum to get this total direction and total magnitude. Now we will move on to the electric field. The definition of the electric field is the force on a charge divided by the value of the charge itself. Since we're dividing a vector by a scalar, the electric field itself is also a vector. We can think of Q0 as a test charge, and it's something that allows the electric field to be measured. If we think of the electric field just due to a point charge, we can show using Coulomb's law that this will equal K times Q divided by R, which is the distance you are away from the charge itself, squared. Conversely, if you know what the electric field is, you can calculate the force on any charge, and it's simply the charge times the value of the electric field. The direction of the force will depend on the sign of the charge. If the charge is positive, it will move in the same direction as the electric field. If the charge is negative, it will move in exactly the opposite direction of the electric field. Now, we use electric field lines to help us visualize the electric field, and as we'll see later, they can tell us a couple of things. They can tell us obviously the direction of the electric field, and they can also tell us the strength of the electric field. Now, an electric field line, it will point in the direction of the field vector at every point. They start at positive charges or infinity, and they end at negative charges or infinity. The more dense the lines, this is where the field is strongest. Here we have a diagram representing the use of electric field lines. We have a positive charge in the middle. We then see some electric field lines. All of them have a direction that points away from the positive charge. This is expected because the direction of these lines is the direction of the field, and the direction of the field is defined as the direction that another positive charge, if placed in this diagram, would move towards. Now we can go to a more complex scenario where we have more than one charge in the system. On the left-hand side, what we have are two charges that are separated by a particular distance. We have a positive charge on the left and a negative charge on the right. As expected, the lines from the positive charge move outwards, and the lines on the negative charge move inwards. In the middle, we have a system where we have a positive charge on the left, and this has twice the magnitude of a negative charge on the right. And what we can see is more field lines that surround the positive charge, and this is one way of showing that the field around the positive charge will have a stronger magnitude than the field around the negative charge. On the right, we have two positive charges that are separated by a particular distance. What we see around each of the charges is, as we expect, we see two sets of lines that move outwards. What we find in the middle of this system is there are no lines, and the reason for this is the electric field vectors will both cancel out to give a zero electric field, and in the middle of the system that will give us no lines. We can also use a parallel plate capacitor to demonstrate the direction of electric field lines. A parallel plate capacitor consists of two plates. One plate will have a positive charge and the other plate will have a negative charge. The magnitude of charge on each of the plates is the same, and they're separated by a distance d in this case. What's of note in this situation is that wherever you are within the capacitor, the number of field lines is usually the same, and since the number of lines are the same, we can actually say that the electric field is uniform, because that is dictated by the number of lines in a particular area. The direction of the lines goes from positive to negative, and if we were to place a positive charge in the middle of this system, it would move from the left to the right. Now let's move to the section on shielding and charge by induction. As we discussed before, when excess charge is placed on a conductor, it is free to move. This excess charge will move as far apart as possible, and this process is called induction. It's demonstrated on the right, where the excess charge is started off in a uniform manner, and it then moves to the surface, and that's where it will indeed reside. Induction leads to something called shielding. So in the process of induction, we find that the electric charge moves to the surface. When it becomes at rest, what one can do is draw the field lines in this situation, and it turns out that when one looks at the field lines at the very center of the system, these field lines all cancel. If the field lines cancel, that gives you a zero electric field, and that's what we mean by shielding. The final section in this chapter will be about electric flux and Gauss's law. Electric flux is essentially a measure of how much electric field passes perpendicular through a surface of a given area. Its definition is equal to the magnitude of the electric field times the area times cos theta, where theta is the angle between the electric field vector and the normal vector to the surface that we are interested in. It will be maximum when both vectors point in the same direction. In this case, theta will be 0, so cos theta will be 1. It is 0 when each of these vectors point at 90 degrees to each other. In this case, theta will be 90, and cos of 90 will be 0. A use of electric flux is in Gauss's law. Gauss's law states that the electric flux through a closed surface that surrounds a charge is proportional to the charge itself. Here we have the definition. It's equal to Q, which is the charge the surface surrounds, divided by epsilon 0. Epsilon 0 is a constant that can be formed from K, which was used in Coulomb's law, and it's equal to 8.85 by 10 to the minus 12 Coulomb squared divided by Newton meter squared. Gauss's law can be used to find the electric field in systems with simple configurations. We have an example on the right where we have a plate that contains charge, and the amount of charge per unit area is given by sigma. We can then enclose this plate with an imaginary cylinder, and we find that the only surfaces of the cylinder that have electric flux are both of the caps. The electric flux through both of these caps will add up to 2 times E times A, and from Gauss's law that will equal the charge enclosed, which is the charge per unit area, sigma, times the area divided by epsilon 0. We can then rearrange this equation to get E on its own. The A's will cancel, and that gives us an electric field that will be equal to sigma divided by 2 epsilon 0.